worried about it. What is the feasible GLS? Now, if the heteroscedasticity form is not known, do you remember when we said it was known? And we dealt with it. Now, if it is not known, as is the case in practice, because in practice we don't know, you got to estimate it. So that omega is not known. Okay? If it is not known, then if you use a known variable, like one of the independent variables, if you use that one of the independent variables, and I'll demonstrate this for you, it will lead to what is known as a feasible GLS. Okay. So the feasible GLS, what it does is that it transforms the variable so that the variable will become homoscedastic. Now look at the feasible GLS. This is a feasible GLS. This is the beta parameter when you estimate it. Now, what is the difference between this feasible GLS and the GLS? Well, you can see that there is no difference except that the omega has a cap on it. The omega has a cap. Now, let me take you back to this one. Look at this one. Okay. The GLS, the omega has no cap on it. That's all. So it means that the GLS, okay, the homoscedastic structure is known. But when the homoscedastic structure is not known, you have to estimate it. And in reality, in real life, you don't know it. So you got to estimate it. Okay. And that is why feasible GLS kind of makes sense practically than the usual GLS. And the feasible GLS, when you apply it, when you're applying it, that is when we say it is a weighted least squares. That is the point. That is when it is called the weighted least squares. So weighted least square is more or less the application of feasible GLS. Okay, that is more or less the application of feasible GLS. Now, what we are going to do is to now do the whole thing in R. And how are we going to do it? Understand the principle here. So we're going to estimate WLS, which is more or less like a feasible GLS. We're going to estimate the model using one of the independent variables. Do you remember we said that you can do the whole thing by using one of the known variables? Okay. Let me just use this one to show you what I'm talking about. So one of the main variables, okay, which is one of the independent variables. As for our work, we are going to use this independent variable known as complement price. Okay, we are going to take complement price, okay, and make it 1 over complement price, or we are going to use 1 over the square root of complement price, just as it was in the model. After multiplying all the independent variables together with a constant by that value, that's 1 over the complement price. So we are going to multiply that all by that. So that means that we need to go through all of that here. So please, I'm just going to demonstrate to you the beauty of that. And guys, remember how it does to the significant levels. Okay. So let's go back to our R. This is our R. Sometimes now I've come to learn to zoom it so that you will be able to see it quite clearly. I am sure it's a bit bigger than we started. Okay. So we are now going to start with this command, multiply all variables and the constant by 1 over the square root of the complement price. So I want you to do that. I want you to type that. This is just an instruction. You can ignore that. Okay. You can ignore that and go with me on what I'm about to do. So we are going to just multiply all of that. That is one way. So we're going to multiply all of that by this. Now, usually you must have your this thing activated. Let me see the command I am. Because when you do it this way, okay, sometimes you will get an error, which is the error that I just got down there. So you need to go and install your mutate function. Let me just take it back. If you have them, you can just do what I'm doing. If you don't have them, later on, you can go through that. Okay. So I'm just going to my command there And then these packages, package number 3 all the way up to 10, you can now install all of those packages, okay, and mutate them and install all of them. Okay. So that is done. Now let me go back to my command. It was 3 something. Okay. So in this command, you can see I have gene multi. I'm calling it gene multi capital W, just to indicate I'm doing a weighted least square. And then the kill, you can see that I've taken a square root of that. I've multiplied the kill by 1 over the square root of complement price. So it is Q divided by square root of C, the price. And I've given it a new name called Q star. Okay. Then the price, I call it price star. Remember when we go to the model, let me just go back and show you. When you go back to the model, it was still star. Okay, so that's what I'm just doing. I'm just doing it Y star, Q star, Y star, and all of them. So I'm just doing it that way. And then you do the same thing for the C itself. Then the location, the occupation, the religion, and all of that, okay? And then you can run that. Okay, now it says that the GW has not been done. So do that first, and then we'll come back to that. So let me take you back to our command center here. We are going to create a feasible GLS for this. And we are going to give a name of the weight called 1 over C. So I told you that there are several weights that you can use. So I'm just going to use one of that weight. So I'm going to use gene multi WLS1, where the weight now is the 1 over the complement price. And then I'll run that result. I'm going to do that here. I'm taking you to R. And then in this R, I'll just look for that command for us to work with. Okay. Well, what I'm going to do is I'm just going to copy that command. I know you all have it. I'm just going to copy that command and bring it to R to estimate it. So let me go up here. Let me just go up here. I'll just type the command just right below this. Fantastic. I'm going to just show you the command just as it's supposed to see. So you have the name as gene multi WLS1. Okay. And then you have everything. The only thing that is changing here is that I've added a weight of 1 over C. So I'm going to run that command. This is the result. Let me just go up. So you can see the results here. And do you remember the R square? The R square, the original R square, I don't know if you can remember it. Let me run the original data just for you to see. And you see the beautiful difference. I'm not going to use Stargazer to do this. I'm just not going to use Stargazer to do this, but just the two of them. Where is it? Well, you can pick any of the original data set. Where is it? Okay, so this is original data. Let me just run this. Okay, and now let's compare the two. Normally I'll use Stargazer, but don't worry. You can see that in this data set, okay, price was only 10%, was significant at 10%. You can see that. Income was not significant. Location urban was not significant. Okay. But when you look at this one, this weighted least squared, where I've just used the complement price to weight, you can see that everything is significant. Okay, so that's a good thing. Okay. So this is what I mean by you don't just say that, oh, price is not that significant, so I'm just going to leave it with that. Because what it means is that there may have been a formulation, a specification of the functional form. And so when there's a specification of the functional form, it will say that price is not significant, when in reality, price is what? Significant. So you got to correct for that misspecification by using things like the weighted least square that we've just done right here. So weighted least square can help you in that regard to be able to correct some of those misspecification issues that one might be having. Okay. Now, so that was weighted least square. That's one form of it. I also indicated that one can use GLS. So in your note, you will see that there is a command you can use to calculate, to load the VLS, what do you call it, the package for the GLS. And this function, what it will do is I will fit a linear model using the generalized least square. And in here, the errors are allowed to be correlated or to have heteroscedasticity. Okay? The errors are allowed to be heteroscedastic. And so we are going to allow that and then use this command to run our results. So we are going to run gen multi GLS, and then instead of the usual LM here, which is the normal one that we do, we will not do that. We'll take a different thing. So I'm going to run that to show you some, again, interest. So these are different modeling that can help a person to be able to get significant outcomes. Let me see whether that is here. And then we can go and show you. If it is here, I don't have to run it. Okay. So that is the one that is down here. Okay. So I'm going to run this command here. Maybe I'll finish. I will just use Stargazer to just show you how the results are looking like. Oh, let me install the package, please. You see that I'm getting an error at the bottom because I've not loaded the NLME package. Okay, so I need to load that package first. Whoa, good. Once that is started, now let me run this. Now you see the results are shown. Okay. So you can see the results. This time it doesn't give stars, but what it does is that it gives you interesting things. For example, it gives you AIC, BIC, ACACI information, BIC, log likelihood results. Those things, we will speak of them later on. But the key points are look at the p-values. Okay, price is significant, complement price is significant, income is not significant, location urban is not significant, but the rest are all significant. So again, this one seems to be showing a similar trend with that of the usual OLS. But then the previous WLS that we did, okay, with that adjustment, that WLS gave us some interesting results. And then, of course, it will tell you the correlations, okay, as far as each particular independent variable is concerned. These interpretations, we'll leave them for later. Okay? But again, that is another model that will help correct. So we've looked at weighted least square, where you take one of the independent variables, this one here. When you take one of the independent variables, and then you divide that through all of them, all of the variables, including itself. And then we've looked at a GLS, where you just run a GLS command. Okay? I'll show you the results in all of them. The next one is the feasible GLS. The feasible GLS. And remember, we said that one focuses on the residuals. Okay? So to do the feasible GLS, we need to extract the residuals of the OLS if there is heteroscedasticity. And guys, you remember that when we did some few analysis, the previous, we were able to detect that there was some level of heteroscedasticity. So we take the residuals of the results. Do you remember our gen multi? That is a OLS. That is a OLS. Okay. So we take that, and then we create the residuals from that. So this command that you see me highlight, this command takes the residuals of the OLS, okay, to obtain the errors of the OLS if there is heteroscedasticity. So let's run that residuals. Okay, I've just run the residuals is here. But if you want to see the residual, you can just highlight those residuals like this. And then you see all of the residuals for each of the 40 observations. So for the first observation, that's the residual, the errors. Please note the errors is the gap between the actual and the predicted, the fitted. That is it. So you've obtained the residuals. Now the next thing you do is you square the residuals and take the natural log of the squares. So now watch it. What I've done is that I've just given a name as log u hat square. Okay, so you see that the u hat, I've taken the square of it to the power 2. This is all in your nose. And then you take the square of the residual. So that's the square, and then you take the natural log. So this command will give us that resource. I've done that. It's gone into the memory of R. Then you regress the residuals. And you can see those write-ups I've done here. You now regress the residual squares. So those were the residual squares in command number 291. You regress those residual squares on the independent variables. And this command will do that. So I'm now creating another command called residual. Okay, this reg u hat is the residual squares. You can see them here. The residual squares that we did and the natural log that we did, that's this one there. Now I'm going to regress the residual squares on the independent variable. So these residual squares, I'm going to regress them on these independent variable, and I'm calling it reg u hat. You do that. Okay. Then I obtain the fitted from that, because from there you can obtain the fitted, the y hat. Okay. So regu hat is the same regu hat here. I take the y hat of that. Okay. And then I can exponentiate the y hat. Remember, this is feasible GLS that we are doing. I will exponentiate the y hat. And finally, I can now come and then watch it. So when I exponentiated the y hat, I now have h hat. Not y hat, but h hat. Now what I'm going to do is I'm now going to do my feasible GLS with this command, 295. And in this feasible GLS command, I am now going to regress the normal dependent variable. Okay, but the weight is going to no longer be the 1/c, which the GLS, the weighted least square was doing, but now the hat, the exponentiated hat, the y hat that I did, that is what I'm going to use, okay, to create the weight. Okay, and then I will re-estimate the model using this weight. This becomes our FGLS model, the one I've highlighted. That becomes our FGLS model. Let me run that. This is our FGLS model. And the beauty of this FGLS model is that it makes everything significant. Okay, it makes everything significant. The R square is slightly higher, and all the independent variables are significant. Every one of them is significant. If you master this, I guarantee you have been able to now understand the superpowers of that. Now I'm going to add some other variables, some other previous commands, okay, to this, because I'm going to now show you everything in a stargazer so that you see the beauty of it. Okay. So now the one that I did before, the one that I did before is the WLS one. You remember the one with the C? Watch it here. I'm adding that, okay, to it. That one we have the results. Then our previous log linear model, that one was also very good. Okay. It had more significant coefficient. I will add that here. Okay. Then there was one that everything was logged. It's one of the old models. I will add that there. And then there were one that we calculated last week, which was a robot Newey West standard errors. Okay. I will add that one there. And so I can now activate my library stargazer. And remember, the library stargazer is designed to help us to put everything in a beautiful table. Okay, I do that, and then I prayerfully show all my results. I hope they all come. There you go. That's a beauty. That is a beauty. That's a beauty. So This is where sometimes you see it in regression in journal articles. They will just pick this and dump it in journal article, and you will see the beautiful results that are here. So watch it. You have the normal OLS, the original one we started with. That one, price was significant. Okay. You can see it here. It was significant. And the significant results are shown down here. Okay. Watch it. So it tells you the significant number. This one, the significant results are slightly different from the standard one. So please note, star gazer are significant. Star is 10%. Star is 10%. Double star is 5%. Triple star is 1%. So note that. So that is why you see the price is significant. Now look at the generalized least square. The price is significant at 5%. The feasible generalized least square, okay, as the name sounds, you can see that that one is what? Is significant at 1%. That is significant. That is cool. Okay. Now the weighted least square that we did was also very cool, as you can see. Is also what's significant. And the most interesting thing is that the value is bigger. The value of the price value is bigger. So there's a negative relationship in all of them. But in the feasible GLS, there is a bigger negative relationship. That is interesting. The same as the WLS. Okay. Now look at the log linear. That one was triple significant, 1%, but then the independent variable wasn't that big. And then the robust, as we know, the robust was also significant. That one will use the same values as the OLS, but it will just correct for the robust standard. So that one, we got to know that all of them were significant before. Okay, so you can see all of that. Then, so I'm more interested in the GLS, the feasible GLS, and the WLS. Okay, the GLS, the feasible GLS, and WGLS. Okay. Please, you just type the name, just ask your question there, okay? So with this, I'm going to ask you a question, an interesting question. Oh, by the way, whenever you are doing this in a paper or thesis or journal, you bring everything like it is here. You dump everything in your work. And then you speak of two of them or one of them that you feel you are comfortable to use them for your interpretations. Okay. And if I were to ask you, which one would you prefer? Oh, the values in the parentheses are the standard errors. Okay. The standard errors. Do you remember I said that the estimate divided by the standard error will give you the p-value? So the values in the parentheses are the standard errors. So those are the standard errors. Those are the standard errors. Those are the standard. Normally, when you divide the upper value, the estimate by the standard error, it gives you the t-statistic. And it is from the t-statistic you get a p-value from which you write your stats, your significance or not. So who can tell me which model you would have gone for? And I will tell you which models I would have gone for. Which of these models, beautiful models, okay, which one would you have used in your interpretation of your finale results? Okay. But remember, sometimes you have it one way, you don't have it another way. So note, okay. Let me see. Just type for me which one you would have used. Just type for me and then we'll later discuss. Okay, so I'm seeing somebody typing FGLS, FGL robust, okay. So somebody says robust, somebody says FGLS. What model, based on your natural understanding of what we are doing, what model would you have selected? Okay, okay. The FGLS is a very, very beautiful model that seems to be capturing. Now, let me tell you something interesting about it. Apart from the price, look at the complement price. Okay. If you look at a complement price, the coefficient is significant 1% like this, like the OLS one. I'm always kind of comparing it to the OLS. Okay. And the values are almost the same. Okay. Somebody said the log linear, not small, but because it's in percentage change instead of the units than the feasible. Yes, you can check it. You can do the log linear, but you see, the log linear one, you are going to have the logs of that. So the way you interpret those ones are also very important. In fact, the way you interpret all of them are important. But the way you interpret that. So yes, log linear is okay. You can just speak of that. Okay. But from the little I am seeing here, okay, I'm going to just take the feasible GLS and compare it with the rest. Now look at the feasible GLS, look at the income. Okay? Income is higher for all of them. It's higher. The weighted least square is good comparatively with the coefficient. So that, I mean, when I say higher, I mean higher in absolute terms. You can see that the income is good there. You can interpret that nicely. But then when you come to the categorical variables, the dynamic variables, you can see that this is higher for the location urban, okay? But this is lower in absolute terms for the occupation teaching. This is slightly lower. Okay? But then when you look carefully at the weighted least squares, it's looking strong, okay? When it comes to this independent variable, you got 44, okay? You got 39, you got 46. So this weighted least square is beautiful, apart from the feasible GLS. Okay? It's almost always bigger than the feasible GLS when it comes to the dummy variables. And then you look at by the swaps here, you can see that the feasible GLS is doing great when it comes to religion, Muslim. Okay? As for their significance, they are all significant at 1%, so I'm not going to talk about that. And then you can see. Now, the GLS in particular, the GLS, the way it is estimated, it carries with it some other functions. Okay? Functions known as the log likelihood, the archaic information criteria, the Bayesian information criteria. Okay, and these are all ways of determining the fitness of the regression. Okay, but we'll look at them at a later time. They are all good, just like the R square is used to determine the fitness. So that is why you can see that it doesn't have an R square, but in place of the R square, it has those values, okay, those independent variables. Okay. Now somebody says that the values are that for the what do you call it? The values under the final one, the robust here. Okay? The person says he thinks those values are the p-values. No, they are still the standard errors. Let me tell you why. Remember that robust measure, it was correcting for the standard errors. Okay, it was correcting for the standard errors. And so the actual standard errors will not be known here. Okay, the actual standard errors will be maybe decimals, but there may be some numbers attached to them. There may be some numbers attached to them. Okay, but because it is taking 3 decimals, so you might not see the other numbers that are in there, but those numbers are there. And so when you divide the estimate by that, it's not going to be infinity. It's going to be a value which is going to lead to a highly significant result. And that is why all of those values are significant, but those standard errors are quite smaller. Okay, they are smaller. They are like closer to 0, but they still have their decimality. I mean, take for example, the standard error here. You might think that this standard error is not that, important, but it is. But it almost became vanished. But there are some more decimals attached to it. So guys, that is a way. This is the interesting way for you to analyze your regression results. And this is just for cross-sectional data. This is just for cross-sectional data. Now, the GLS, the feasible GLS, when you get to the panel data regression, you see that that one is brother, is sister, is what is known as a random effect model when we come there. So we'll be discussing those ones at a later time. But the beauty of this is this feasible GLS and the weighted least squares. All the estimations that are there in the slides, so you can check it, and then you can come with your own situation. But this is beautiful. This is a way you get all of the interesting results that we have. Okay. And then you can produce this beautiful table that we did using this type of design. And then you can have these fine results also in there. One last point on feasible GLS. Under the feasible GLS, okay, the constant becomes the H cap. It's not an H, but an H cap. But we are told that it's always nice to be careful with interpreting the slope coefficient. Use as the weight. Okay. Because when you look at it, they were multiplied by some values. So the weight becomes like intercept of the model and vice versa. So when you are interpreting it, one has to be careful. We'll look at the interpretation later. We'll look at the interpretation at a later time. Let me see what one of you has indicated. How do you copy this table to Word? Oh, it's very, very simple. Let me just do that. This one is a normal copy and paste. But if you want to do it in Excel, it's a different thing. Okay. So let me just copy it as it is here. So this is the results there. I'm just copying. I'm copying. Let's go down. I need to just scroll it. Okay. Let me just. Okay, so unfortunately, this has copied everything, but then my interest is here. All right. But let me assume, because normally if I want to copy it, I need to zoom out, okay? I need to zoom out. So you can just pick a zoom out and zoom out, okay? Just to get a whole result, zoom out. And then I can now copy everything as it is. Okay. I've done the copy. Let me take you to any word situation. So this is a Word document. I hope you can see that. So you can type anything you want to type in the Word, okay? Anything you want to type in the Word, okay? And then you can paste it just as it is. And you can see the way I've pasted it. Okay. That's it. You can now reduce the size and the way you want to reduce it. Some of them may slightly eat into others, okay, but you've labeled them. Okay. You've labeled them. Other than that, you can see clearly that majority of them are in that formatted order. So you can now take your time and format it like this. Okay. And then you can speak of it. Okay. You can reduce the size. Another thing, sometimes some people will do is that they'll take it to Excel. Okay. They'll take it to Excel. And the thing about Excel is that sometimes it does arrangement nicely. When you take it to Excel, let me just show you what I'm doing slightly in Excel. When you take it to Excel and you try to do data, text to columns. Let me see. Text to columns. Let me see how it looks like in the space. Okay. And then I just hope that looks good. So once you have it like that, oops. By the way, the one I did by copying it into what do you call it, into the Word, you can see. But this what do you call it? This one also organizes it in that way, in some slight way, the way it has to be done. Sometimes there are some anomalies, but I like to copy it directly. Okay? I like to copy it directly to Word, just as I did, and then adjust it in the best possible way you can. So when you look at this, another point you want to notice this. that you can use the feasible GLS or the weighted GLS plus the log of the variable. So that's it. When we were using the feasible GLS, we didn't add any log, if you can remember, no logarithm. But we are saying that when there's a need for you to use the log of some of the variable, no problem. You can go ahead and incorporate some log. Okay? You can incorporate some log functional form, just to produce homoscedastic errors. Okay? Now, so that will handle most of this. Okay? And also note that we've said this before. Instead of the feasible GLS, we said it many times, you can still go ahead and use your OLS, which we did, and then correct for the standard errors, which we did, using the heteroscedastic autocorrelated consistent standard error, which is sometimes called the Newey West standard error. So that one will correct for the heteroscedasticity and the autocorrelation for you. But we said before that when the sample size is large, then it becomes much more sensible. Okay? When the sample size is large, then it becomes much more sensible. Ladies and gentlemen, that brings us to the end of the entire caboodle when it comes to heteroscedasticity, how to spot it, how to deal with it, how to check it, how to test it, and all of that. One can now look at this situation and be able to do it. Once you know the problem it causes, once you solve it, you see that those problems are not there again. And that's a beautiful way to conclude our study.